Hello everybody, and welcome back to Ask Math Anything. If you haven't been here before, I'm going to welcome you to a strange session where we'll see people ask questions, and I'll answer some of them, and I'll not answer some of them. How do we decide? Well, I choose questions to answer that are based on what I think might be able to turn into good stories for people who are learning algebra or geometry. Now, as you are making these questions, please ask whatever you're interested in. I love this chance every day to go and talk to people from all over the world who maybe have questions that they have about math. If you've been here before, welcome back. All right, let's go ahead and dig in. What should we talk about today? Yes, it's true. Xiaolin Wang, I was late. I'm sorry. As some of you may know, I'm also working on an app to try to stop the spread of COVID-19. So my life basically switches between working on that and then suddenly being like, oh, it's 4 o'clock p.m. 4 o'clock p.m. Eastern time. I better run up and say hello to all these people on the internet. Okay, what do we have here? Oh, okay, let's try this. So I see a question here that I want to play with. And this person wants me to not use a calculator. Huh. So this person says, the numbers are very important. It's by Akash Sarodi. And Akash Sarodi says, all right, we have two numbers. 5, 9, 3, 0, 3, 4, 5, 1. Okay, and this is one number, and we also need to multiply it by a number that has how many nines? Counting is really hard. Let me see. What does it say? It looks like it has 8 nines. 9, 9, 9, 9, 9, 9, 9, 9. And we're supposed to multiply these. How can you do that? Who likes multiplying huge 8-digit numbers? Anyone want to multiply this? This looks terrible. If you want to multiply it, you do all kinds of stuff and add. But there's a trick. The trick is that's a lot of nines. A lot of nines looks a lot like 1 with a lot of zeros. So what this means is that it's the same as 5, 9, 3, 0, 3, 4, 5, 1 times 1 with 8 zeros. This is why I wrote the number very carefully. I really wanted to know how many nines there were. And here I chose to draw the commas every 4 just because I want to emphasize there are 8 zeros. Some of you are more used to drawing commas every 3, but whatever, it's fine. So is this easy or hard? Well, actually, what happens when I multiply by this thing with 8 zeros? It's wonderful. It just shifts it all the way across. This first part is going to be 5, 9, 3, whatever, and 8 zeros. So I like this. This is going to be 5, 9, 3, 0, 3, 4, 5, 1, and then 8 zeros, minus 5, 9, 3, 0, 3, 4, 5, 1. I know that the person who asked the question wanted you to do it in your head, but I just want to show you how I'm doing it in my head. I mean, this is actually what I would do. What I saw when I saw this question is I said, aha, I think all we're going to do is we're just going to write down that number and then write down what happens when write down that number but take 1 away from the end. And then just take every one of those digits and do 9 minus it, right? That's all that you have to do. The answer to this whole thing is running into my head, but I'll duck. So the answer to this is 5, 9, 3, 0, 3, 4, 5, 0. Don't forget that you had to borrow for that one. And then you just take 9 minus of everything, except the last digit. The last digit is 10 minus. So, 4, 0, 6, 9, 6, 5, 4, and 10 minus 1 is 9. I know you usually subtract from this side, like 10 minus 1, you'd get 9, but I knew I would be borrowing all the rest of them, so I'd be doing 9 minus on all the rest of them. So I think this is the answer. Does this match what we see in the chat? seems like it's reasonable. And in fact, you didn't need to write all this down. As soon as you saw that there was the same number of 9s as there were digits up there, it was already obvious that all you have to do this is just to take the top, take the number, take 1 away from the last digit, that's here, and then rewrite that number where you take every digit subtracting it from 9, except the last digit you subtract from 10. That's it. Okay, well, thank you very much. This was a very, very fun question to start today off with. This is good. More questions. Oh, neat. Somebody asked, if you converted pi into music, where each of those digits was a note, what would it sound like? I think it would sound kind of random. But why I say that is because many people think that the digits of pi look very random. And there are notions of what does that mean to look random. It means that somehow every digit appears about 1/10 of the time. And in fact, if you look at pairs of consecutive digits right next to each other, you'll also see each of those pairs appear approximately 1 out of every 100 times. So you'd basically sound like somebody, here's what it would sound like. It would sound like a monkey playing on a keyboard. Except even more random than a monkey. Because when a monkey plays on a keyboard, that's first of all, that's sort of like me playing on a keyboard because I don't know how to play the piano anyway. But the way oftentimes a monkey or a person would play is that they play a lot of notes kind of around each other. But you'd actually end up getting things that are like bouncing far sometimes, close sometimes, far sometimes, close, completely random. And that's what pi would sound like. All right. Yes, I see that people are now putting all of these things. Susan Shu thinks that Bob the cat would be more random. You guys are good. More questions. Oh, Laser Shadow, you've asked a question that we've answered in a previous live stream, so I'm just going to tell you the answer and leave it to you to play a little bit. You said, true or false? If false, provide a reason. If an irrational number is raised to an irrational power, the result will always be irrational. And the answer is it's false. Actually, it's possible to go and take numbers and raise them to other things to get like really weird numbers. And just to give you an idea of what the answer was, you can take square root of 2, and there is something you can write there where the answer is 3. And whatever thing you write there is actually going to be irrational. And we talked about this before, so I won't go and hit this again. Oh, Joshua Wu says, that was my problem. Yes, so you know what? Joshua Wu, maybe in the chat you can maybe explain a little bit to the person who asked this problem. But we won't go into it today because we already talked about it on this live stream. Okay, more questions. This was to Laser Shadow, by the way. Mathletic Athlete 21. Po-Shen Loh was late by n minutes. What is n squared? I'm not sure how many minutes late I was. Maybe I was late by about 3 minutes. Maybe. I'm not sure. I lost track. 3 squared is 9. I can tell you why I was late, though. The reason is because we actually record all of these live streams. We don't know if we're going to do something with them at some point. And when we record them, we have 2 different memory cards. And one of the memory cards takes, for some reason, a very long time to format. And so that was the one that was the primary memory card in the camera. And so when I pressed format, I actually thought I was formatting the fast format one. And when it started chugging and chugging, I said, oh no, what happened? And it turns out that it was the slow formatting one. When I do the fast formatting one, I can just format it really quick, then click like start formatting the other one, and then already press record and come over here and talk. All right, more questions. Somebody asked, what Intel generation is it? The memory cards are using CFast. It's like CF is compact flash. They're all CFast cards. Because actually what we record here, all of the stuff we do here is produced in the same studio that we use to make the daily challenge classes. And for that, we use some fairly high-end recording equipment. So actually the recording that we're making right now, it uses 250 gigabytes every minute. So every minute it records approximately 4 gigabytes, actually more than 4 gigabytes of storage. So it actually has to be a pretty fast card. Okay. Ooh, we got some new people here. This is pretty good. Huh. Oh, I want to try this one. It's a question about Fibonacci's. And I also saw somebody asking about Module 6. Yes, we actually definitely do want to record Module 6. The only problem that happened right now is that because of COVID-19, my first priority became to stop the second wave. Some of you live in the United States, and you may know that we are potentially going to have a huge explosion in COVID-19 cases soon. And so what I'm trying to do right now is to prevent it from happening, because if that happens, it's going to be very bad for everyone here. All right. But I see there's a question here which is about math, and I don't know the answer, so I'm curious. The nth number of the Fibonacci sequence, and this is from Adi Singh. Adi Singh is saying there is a number which is the nth number of Fibonacci sequence it just so happens to be n squared. What is n? Okay, so now I'm not entirely sure how to answer this because I never know what is the first number of the Fibonacci sequence. You see, because if the first number of the Fibonacci sequence is 1, then I guess it would work, right? If the first number of the Fibonacci sequence was 1, then 1 is 1 squared, and so we're in good shape. But we don't quite know whether that's what they mean. So what I'll say here is I know that whatever it is, though, it'll be a pretty small n. And the reason it's a pretty small n is because of the fact that the Fibonacci sequence doesn't grow quadratically. It grows exponentially. What I mean by this is quadratic is actually quite slow. If you went and plugged in 100, you would get a mere 10,000. 100 squared is only 10,000. But if you put 100 into Fibonacci, you get approximately 1.6 to the power 100. And that's huge. That's like bigger than that famous story about like the person who started with 1 grain of rice, and then every day the number of grains of rice doubled, and 1 month later it went kaboom. If you actually take 1.6 to the power 100, it's huge. It's huge. It's like 200. It's like 2.56 to the power 50, which is way more than those grains of rice. It's just a huge thing. So that's how I know that we don't have to worry about a huge n. So actually what I'll do to figure this out, since I don't know what you mean by n. Oh, I see. Anna Howe says that was a legend, too, about the grains of rice. But let's go and list some Fibonacci numbers. I'm guessing that the person who made this problem was thinking about the fact that there is an interesting Fibonacci number that's a perfect square that happens later on. So I don't know what is the first Fibonacci number, but I'm going to write down the sequence. 1, 1, 2, 3, 5, 8, 13, 21. None of these are perfect squares, except for the one. 34, 55, 89, and then 144. And that's nice. I just happen to remember that the 144 shows up. And so if there's a 144 there, I wonder if that's the 12th one. And what I mean by this is that it's not clear. It's never clear what's the first number in the Fibonacci sequence. That's why usually people tell you, let's suppose that the first number in the Fibonacci sequence is 1 and the second one is 2, or something like this. But I'm going to guess that the problem wants the answer to be 12. Because actually, if you keep going, it goes to 233. It's not very nice stuff. 12, 11, 10, 9, 8, 7 is 13, 6 is 8. Ooh, the fifth is 5. 4, 3, 2. Oh, look at that. So actually, there are 2 answers. So that means that the answer is, it happens to be a 1, or it happens to be a 12. Now you might ask, how do I know that, can 1 work? Springfield Chinese has asked, can 1 work? I would say that 1 works, I would say in this problem, 1 squared is 1. And you know what else? Do you know what is the 0th number in the Fibonacci sequence? The 0th number in the Fibonacci sequence is the number that you'd put there so that that plus 1 equals 1. Ah. So now I would say, okay, most people don't say the Fibonacci sequence starts at 0. But I would actually say that for what I do, I usually find it very convenient to say that the 0th Fibonacci is 0, the first Fibonacci is 1, and so on. And so that happens to work well. Ooh, Pietro has asked, how do you prove it's an exponential growth? What's the easiest way I can use to do this? Well, here's what I could do. Is that what I could do? I think that might actually work. Or might it work? Oh, it's really quiet now. You're saying it's really quiet now. That's because I'm kind of thinking to myself. It's like, how would I go about proving that it's always going to be an exponential sequence? So I'm basically thinking of, if I wanted to do this, 1.1 plus 1, 2.1 versus 1.2. Yes, I can do it. You can use induction. Okay, so first of all, I need to explain why I would expect it to not give me more of these numbers. And the reason I don't expect to give it more of these numbers is because this thing is going to be going faster and faster. So first of all, there's this green graph that I want to graph, which is the Fibonacci's. Okay, the Fibonacci's are going from 0, 0, so at 0, 0, it's 0, at 0 it is 0, at 1 it's 1, at 2 it's still 1, at 3 it's 2. Do you understand what I'm drawing here? This is a graph. I'm just kind of graphing these green numbers. 0, 1, 1, 2, the height is like whatever that number is, and suddenly it goes to 5. Oh no, it's blowing up. And then the whole thing flies away. Okay, so I got the sequence, and somehow this sequence, apart from the beginning ones, kind of looks sort of like, whee, it flies away. So it goes up very fast. Yeah, I drew a bunch of rocks, I guess. I just drew a bunch of rocks on this graph, and I'm connecting all those rocks. And that happens to be Fibonacci's. And then there's another graph. The other graph happens to be something like y equals x squared. And the y equals x squared is what you'd see with the nth number being n squared. And if you zoomed out, here's what you see. Fibonacci, let's draw another axis. Fibonacci, so let's draw the other normal x squared first. Normal x squared is like, it's getting bigger. So this is like x squared, or n squared, since we used n. Let's go ahead and use n squared. And then we got our Fibonacci game going on here. Fibonacci kind of starts slow, but then it goes through here. Oops, it's supposed to be green. Fibonacci starts slow, goes through there, and then suddenly it blows up. So that's Fibonacci, okay? And now that's because Fibonacci is growing exponentially. It's multiplying by something and multiplying by something. And eventually it multiplies by too much. Because somehow when you grow with the multiplication, it just blows up really fast. And now people are asking, what's the question? Pooja is asking, what's the question? The question is, how do you know that Fibonacci grows exponentially? Well, here's how you know. You can say that eventually, actually not very eventually, almost immediately, it's bigger than 1.1 to the power n. Right? Do you agree that 3 is bigger than 1.1 to the power 4? That's like obvious. Okay, so here's 2. 2 happens to be bigger than 1.1 to the power 3 also. So what I'm saying is, if I had 1.1 to the power 3 and 1.1 to the power 4, something bigger than each of those, whatever the 5 is, has to be bigger or equal 1.1 to the power 3 plus 1.1 to the power 4. Right? That makes sense. The reason it makes sense is because the 5 is just that one plus that one, and each of them is bigger than 1.1 to some power. But now what will I do with this? If I have this, I want to compare this to 1.1 to the power 5. The way you do that is you factorize out 1.1 cubed. It's 1 plus 1.1, which is 1.1 cubed times 2.1. That's important because 2.1 is bigger than 1.1 squared. 1.1 cubed times 1.1 squared. And that is 1.1 to the 5th. So I just wrote a big long chain of yellow inequalities. But what I just showed is if the 2 is bigger than 1.1 cubed, and the 3 is bigger than 1.1 to the 4th, then the 5 is bigger or equal 1.1 to the 5. And what this shows is whenever I have 2 of these that are already bigger than 1.1 to some power, then the next one is bigger or equal 1.1 to the next power. And so that goes on forever. This is called mathematical induction. What I'm saying is that as soon as I have 2 of them in a row that are bigger than 1.1 to the appropriate number, then the next one will be 2, and the next one will be 2, and it goes on forever. And that's the proof of why this is always bigger or equal 1.1 to the n. I mean, eventually. This is all eventually bigger than 1.1 to the n. And that's why it grows exponentially. Okay, more questions. Oh, Pietro says he remembers now. There's a closed formula for the nth term, and it involves the golden ratio. There is actually a closed formula. The answer to this is that this is something like golden ratio to the n. Oh, this just made me think of something. I can tell you the formula. And this is the formula, okay? Nth Fibonacci. Hey, this is a problem I gave on my exam. So I teach a class at Carnegie Mellon University. Students take the class. And in the first year, I think, that I taught the class, I put this question on the exam. It's a true or false. True or false means prove it or disprove it, okay? And Fibonacci number is e to the power n divided by 2, and then round up. Oh no, come back. Okay, round up. Let's try this out, okay? So this is a really interesting formula. By the way, do you know what E is? E is this number, a very special number in math, appears everywhere. 2.718284590. Oh, no. More 1828. 1828459045. Okay, so I have this nice formula, okay? This nice formula for the nth Fibonacci number. And if you want to test this out on a computer or on Wolfram Alpha or on your smartphone or on any old calculator, just take e raised to some powers. Let's try it out, okay? So what happens? Let's make a chart. N, and this e to the power n over 2, round it up. Chart time. Actually, you know what? Let's do e to the power n over 2, and then we'll round up. Round up. All right, let's start. So when n equals 0, I guess I'm maybe off by 1 here. When n equals 0, e to the power 0 over 2 is e to the power 0. That's 1. That's obvious. And you round up is 1. Okay? If n equals 1, so here, I guess over here, I'm like a little bit off on the Fibonacci's. It's not that the nth Fibonacci is that. Maybe it's the n plus first Fibonacci, but we'll find out soon. Can anyone tell me what is e raised to the power 1/2? Anyone got a calculator? Yeah, so yes, thanks for asking. So the 0th Fibonacci is 1. You know, I don't really like that here. So I'm going to say we're going to do n plus first Fibonacci, okay? So let's just adjust it this way. N plus first Fibonacci. Not nth, n plus first. It's the n plus 1th, which is the n plus first. Okay? And so now, 1.64. That's the next one. 1.64 round up is 2. Oh, you know what? I want to use the same color. I want to use alternating colors. I find it easier to read. 1. 1.64. 2. Great. What if I put a 2? Oh, I know that. That's e to the power 1. That's 2.718. Okay, so round up is 3. Oh no, that means that this is not the n plus first. 1, 2, it's the n plus second Fibonacci number, okay? Sorry about that. N plus second Fibonacci. Let's keep going, okay? N plus second Fibonacci. So the next one is going to be 3. Okay, what happens when I take e raised to the power 1.5? Who's got a calculator? And e raised to the power 1.5. I do need some people who can put an answer here, or else I might have to go and grab my calculator. 4.48. Okay, we'll go with 4.48. I hope you guys are right. That's 5. Okay, next one is e raised to the power 2. What's e squared? Because it's e to the 4 over 2, e squared. What do we have here? 7.389. 7.39. That makes 8. Next, the fifth one. You guys know where I'm going with this. Fifth one is e raised to the power 5 over 2. That's 2.5. What's e to the 2.5, everybody? I have ooch. You gave me that one. Yeah, people are saying just multiply by square root e, but I don't know what that is. So 12.1824. I'll just call it 2. Well, let's call it 1824. So 12.18. That goes to 13. And 6. What's e cubed? Anyone know what is e cubed? E cubed. It seems to be working, says Pietro. E cubed, 20.085. 20.09, let's just say. 21. Hey, what do you think? Do you guys like this? Is it true or false? What do you think? Is this true or false? Hey, look, somebody, I have Ooch, said 3301. 7th one, 34. It's amazing. It's amazing. So it looks like it's perfect by mathematical lumpdunction. It's true. And, you know, I'll tell you a little bit about the story of how this happened on my CMU exam. So on somebody said it's 55 next. Look at that. Next one's 55. And so on my Carnegie Mellon exam, like that particular exam, I don't even know what this number. Oh, 54.5, 54.60 it looks like. Right? So we got this thing here, and you know, I put on the exam, and after I put in the exam, I said, hey, actually you can use your calculator. On this exam, I let people put their calculator in. We have no space for 9. 9 doesn't fit. You see, there's no space down here. We can't plug in 9. But, oh, wait, what? 54? Are you sure? I think this one's okay. E to the 4th power. But on this exam, you know, I went and said you can go and put in, you can use your calculator. And I saw a lot of people work this thing out. But unfortunately, this is a classic example of it works for a long time. Unfortunately, the next one is 90.01. Uh-oh. Oops. Okay. So unfortunately, actually, this thing breaks. It's not true. It's not true that it's e raised to the power n over 2. But you see, this is actually an example of a very, very good exam problem. It's because, in fact, in the class, we had already proved in the class that the Fibonacci number is not this. No, so this is false, false, false. Do not try this at home. This is false. So, but it turns out that we had actually, in our class, we have already proved in our class a different formula. In our class, we actually had proved, so in class at CMU, Carnegie Mellon University, I had shown a formula that looks something like this. It was 1 over the root 5 times 1 plus root 5 all over 2 raised to the power n, round. Not round up, just round. I had showed that this is actually a formula for some like nth or n plus first Fibonacci number. I always forget which one it is. And so we actually knew this. So you see, if you happen to know this fact, then you know, oh yeah, that's the golden ratio. Let's use yellow for it. This number here is the golden ratio. So if you happen to remember what we had learned in class, then you would know that the Fibonacci number is supposed to be something like this golden ratio to the power n, in which case it's impossible that this would work. Because if this worked, this is like square root of e to the power n, right? If this is square root of e to the power n, and this is the golden ratio to the power n, there's no way they can actually match forever, because the golden ratio and e are different numbers. And eventually one of them makes too much deviation from the other that it's over. So actually this is a great exam problem, because anyone who remembered this, they would just take their calculator and say, there is no way that can work. No way. And they would just go and try big enough numbers until they were done. And, big enough numbers, and there it is. It's done. On the other hand, if you don't know this, then by the time you write out the first 5 or write out the first 6, you might think, gee, looked really true. And then you would not be able to solve the problem. So this is an example of a problem which, if you know how to solve it, it's done. And you just use your calculator to be done. And if you don't know how to solve it, well, then it looks really, really deceiving. I don't want to take credit for coming up with this question. I actually found this question in a beautiful book on discrete mathematics, which was written by Laszlo. Wait, just a second. Let me make sure I have that right. I think it was Lovász, Pelikan, and Vesztergombi. I believe so. It was 3 Hungarian mathematicians. One of those Hungarian mathematicians is actually the current national coach of the Hungarian International Math Olympiad team. and the other two are actually extremely famous researchers in mathematics too. But this was a book that I found this particular problem in. And something that's worth knowing is that I believe this story is that they wrote that book while they were in college. So they were in college, and I guess they decided that they wanted to write a book to introduce combinatorics to all kinds of people. All right. So this is an example of what not to do. This is what you can do. And this is how dangerous it is to look for a pattern and think that a pattern will work. Let me take another question. So I saw Jacqueline Zhou asked, how did you meet your wife? And you asked so many times, I'm happy to answer. And actually also because I just talked about college. I met her on the first day of orientation, the first day of college. So that's how. Okay, more questions. Or maybe it was lots of people who asked that question. All right. Luke Wang said, Po-Shen Loh said that the live stream will finish in 10 minutes. But someone asks a Lexington math competition question. If n is how overtime Po-Shen Loh is, what are the chances that n is 0? Very low. Yeah, unfortunately, very low. The Lexington math tournament questions are very difficult. And my style is if I start doing something, I kind of like to finish it. Okay. Anna Howe has asked, who is your technical team? You must be referring to technical team on Novid. Technical team on Novid is a lot of really interesting people with different talents. We have some people who are really, really good at math, some people who are really, really good at algorithms so that we can calculate with like 1 billion people's data if we needed to. We have some people who are really good at design. And design is not just making pretty pictures. It's something where you try to figure out what someone actually wants to use that smartphone app for. And then you make it so that it's easy for them to do what they want to do. We, of course, also need people who are really, really good at outreach. Because what we're trying to do right now is we're trying to help people all over the world know that, for example, if the app that your city or your state or your government made doesn't work, well, we got a solution. Or maybe not even that. Maybe they're not even making such an app. We're trying to help everybody come in. So we got lots of different people on this team. Okay. Ethan Gunn. I come from a mine and get surrounded by wood always. Everyone uses me. What am I? What kind of a question is that? I come from a mine and get surrounded by wood always. Everyone uses me. What am I? It looks like it's a puzzle that's not really quite mathematical, but I was curious. Surrounded by wood always. Coal? I mean, I thought that might make sense, might be coal, but somehow coal, I don't use it. Minecraft. Yeah, it sounded like Minecraft to me, but it said, I come from a mine and I get surrounded by wood always. Everyone uses me. What am I? Maybe it's coal? Maybe it's graphite. Pencils use graphite nowadays and is surrounded by wood always, and everyone uses me. But I don't. I actually use this thing. This thing's not a pencil, although it can write. So I don't exactly know the answer. I'm going to guess that it's something to do with maybe pencils. Let's see. So I don't completely know what's the best answer to this question. But if somebody else knows, you guys are welcome to type in. And it does sound like pencils. It does sound like a pencil might work. Surrounded by wood always. Okay, more questions. Oh, okay. Let's try this one. I'm wondering if there's a way to save some time on this question. Okay? So it's a math question. And this math question says, hey, I have a sequence of positive integers. It is 2. Wait, let me tell you what's not in the sequence. There's no 1 in the sequence. Well, that looks like an asterisk. Let's do it like this. There's no 1 in the sequence. But there's a 2. There's a 3. There's no 4 in the sequence. There's a 5. There's a 6, there's a 7, there's an 8. Guess what? There's no 9 in the sequence. but there's a 10. There's an 11. Hey, can anyone guess what sequence I'm talking about? So I have a sequence here, which is going to have no 1, no 4, no 9, exactly no perfect squares. But the question is not that. The question is, what is the 20/20th term? What is the 20/20th term? Okay, how about you go and try to think about this question? Don't just try to list all of them. That takes too long. Instead, I think something that could be useful would be to say, maybe we should just go and say from 1 to 2020, how many X's did we draw? How many did we strike out? Oh, Skylar Shreya says this problem is from Armel. And Samuel Ding says this was probably made in 2020. I'm with you on that. And so let's go and find out. It's like, so how many squares would I have if I went all the way to 2020? 2020, by the way, is not a perfect square, but soon 2025 will be. 2025 is 45 squared. So that's good to know. 2025 is equal to 45 squared. So what that means is up until 2020, over here, I have removed 44 of them. Well, if that's the case, it's easy. Just add 44 more terms, right? Because if I went to 2020 and I have removed 44, let's just add 44 more terms to 2020. So if I now go from 2021, oh, I have no space because we are running into the corner. Ooh, I want that back. So, okay. Now what I have to do over here is I need to say plus 44 more terms. That was supposed to be an exclamation mark. So how would I do that? I just go answer 2020 plus 44, right? Ah, but there's a trick here. Not quite. Because actually if you add this together, you get 2064. And unfortunately, there's one more thing you're knocking off, 45 squared. No, 2025. Thank you, Mathletic Athlete 21. So not quite. Remember, 2025 is out. So let's go with plus another one. And that's running into my head. But that's 2065. I have to go and check, do I need to worry about the other one too? Do I need to also worry about the next square? What's the next square that's bigger? That's 46 squared. How big is 46 squared? Well, here's an easy thing you can do. It turns out that if you want to have the next square, you can actually do this. You take the 2025, and then you plus the 45, and you plus the 46. And that's how I know I'm not going to have to worry about this. Because I'm only doing 2020 plus 44 plus 1. There's no way I could get all the way up to 2025 plus 45 plus 46. I don't even need to calculate that. Because I'm just adding not enough. This is less than what I'm adding there. So that's the answer, 2065. Hopefully that's the answer to this question. What? The answer is 2067? Uh-oh. Really? So if the answer is 2067, then I got it wrong. So now I'm a little bit curious. As you know, if you watch this live stream, you know that I typically do get things wrong. But we'll go and ask our crowd of 200 plus people. And so we will see if people think that it seems okay to be 2065. And if you think it's 2067, I'm a little bit curious what else that I have missed. But I think this is right. Okay, see, a lot of people have said 2065. This is clearly how you do math, right? You go and ask people for a popular vote, and you go and see what's the answer. Well, it works if you have a lot of people who are pretty good at math. By the way, do you know why this is true? Do you know why if I want to go from 45 squared to 46 squared, it will go to here? There's an easy proof by picture, if you want to know why that one's true. I just always think of it this way. See, here's 45 squared. 45, 45. And the area is 2025. Now if I want to go to 46 squared, all I do is I add a 45, right? And then I also add a 46. Boom, that's it. So this is actually how you know from 45 squared to 46 squared, you just go by plus a 45 and plus a 46. And that's it. So that's, yeah, I have Uch says, that is cool. Yes, this is not like some crazy fancy formula. This is actually just pretty simple. It's just like a proof by picture. If you prefer proof by formula, there's also a way to do proof by formula where you just multiply things out. The proof by formula, maybe I'll fit it right here, is that if I try to do an n plus 1 squared, that's always equal to n squared plus 2n plus 1, which is equal to n squared plus n plus n plus 1. But I personally prefer the proof by picture because I can just see it. Okay. I think that's pretty good for this particular problem. Thank you for asking the question. Why are you asking all these questions about whether I like my wife? Of course. And who is my wife? Well, I'll let her not necessarily reveal herself unless she wants to. Okay, great. Let's ask some more questions. Okay, more questions. Let's go back to math. Ooh. Somebody asked me, what's 13 to the power 12? 13 to the power 12 is a huge number that I don't think I want to work out. Why I say that is because if I even wanted to work it out, what would we do? If I wanted to know what is 13 to the 12th, here's what I would actually do. I would do 13 cubed, and then I'd square it, and then I'd square it. But the number is going to be pretty big. It's not going to be much fun. So let's not do that. Okay, more questions. Yue Cai Zhu asked, when will Po-Shen Loh retire from CMU? Not for a while. I love it here. I should say, when you guys are applying to college, however old you happen to be, I will probably still be at CMU. And you'll be able to tell because I live stream all kinds of stuff anyway. But this is a great university for people like me who like to do crazy things. And I think that I and CMU get along very well. And so by the time you apply for college, I'll be here. Okay. Here's a kind of a question that I want to just hit quickly. I like this one too. It's a math question. It says, here's an equation. The equation is 3 less than square root x less than 3.6. Find sum of all the x, all positive integers x. Oops. All positive integers x that satisfy this thing. This is a quickie. Whenever you see something like this, you go and say, all right, well, in that case, what do I know from this piece? In order for the square root of x to be bigger than 3, I need to have that the x is bigger than 9, right? That's what that constraint tells me. So I need that piece. I also need this piece. This piece tells me that x is less than 3.6 squared, whatever that is. And I'm going to write an and here. The reason I'm going to do that is because sometimes when I have this like compound inequality, you're not really sure how to interpret each side. You don't always square both sides. This is why I wanted to use this problem. Let me show you something you're not supposed to do, okay? It is not okay to try to solve problems like this, to say, hey, let's find all of the numbers where minus 4 is less than the square root of x is less than 2. You know how I'll do that? I'll square both sides. And I'll get 16 less than x less than 4. So I just need to go and find out all of the x's that are 16 less than x less than 4. There aren't any. There are none. None. No solutions. No solutions, right? No solutions. So I'm done. There are no x's that work. Does everyone agree with me? Does everyone agree with me that there are no x's that work? Well, actually, I think 0 works pretty well. Actually, so does 1. So does 2. So does 3. So where did we go wrong? How come I'm not allowed to square both sides? See, why I'm saying this is because some people said, oh, this is trivial, this is easy. I know that some people in the chat think that this is easy. But the way that many people do it is they say, I just square both sides. And I'm showing you that that doesn't work. Square both sides is not okay. In some sense, it's because negative went to positive. But it's also because what this means is it means and. Whenever you see two of these things, it means the first one and the second one. So if you want to go and translate them into something, the first one happens with this, and the second one happens with that. So I just split them. That's why I split these two, and I wrote and. Okay, whatever. But if I wanted to do this, now I need to know what's 3.6 squared. I happen to remember that's 1296, I think. I think that's 12.96. Less than x. So now I just need to know all the x's which are between 9 and 12.96. Now I can do it. When I take this thing, I find out that x equals 10, 11, or 12. Oh, here's another trick. What's the fastest way to add these three numbers together? If you saw 10, 11, and 12, how would you add them together? You said 33. How did you get 33? I'm a little bit curious. Whenever I see three numbers like this in a row, exactly, Mathletic Athlete has an athletic trick, and so do several other people. You take the middle one times 3, because they're equally spaced. So if I want to add 10 and 11 and 12, it's so much faster to say it's just 3 times the average one. So the sum is equal to 3 times the average one, which is 33. And that's the answer to your question. Okay, more questions. What else do we have here that people asked? Good gracious, it's 4:48 already? Our time is running out. Okay. More questions. These kinds of problems. Let's do this one real quick. All right, how do you guys think of all these settings anyway? So what you're saying, Pooja Meiti has said, 3 cats catch 3 bunnies. In 3 minutes. How long for 100 cats to catch 100 bunnies? I will say we saw something like this before. I see also Mathletic Athlete is asking, since when did cats catch bunnies? And then also Susan Xu says, one must ask, what happens to the bunnies that the cats catch? I think there's the other question also, which is, are cats capable of catching bunnies? You know, I have a question. Which is faster? I'm a little bit curious. I'm not really sure that cats can catch. Well, you know what? Maybe I'm just very ignorant. I don't have any cat pets. Does anyone happen to know what is the relative speed between cats and bunnies? Does anyone know what's faster? I remember hearing these like fast as a rabbit. I never heard someone say fast as a cat. What is actually faster? Does anyone actually know? Bunnies are faster, right? So if the bunnies are faster, the answer is like, it should be infinite. Oh, I see everyone already seems to have figured out the answer. Is it 3? Let's find out. Let's just do it real quick, okay? So actually the answer is 3 minutes. The answer is 3 minutes because somehow if you have 3 cats catching 3 bunnies in 3 minutes, then somehow you just go and scale the cats and the bunnies first, right? If 3 cats catch 3 bunnies, 1 cat catches 1 bunny, apparently, in 3 minutes. And so if you scale, you would scale these at the same rate while leaving the same amount of time. That's how I always think of it. So if I had 3 cats catch 3 bunnies, then you have 100 cats catch 100 bunnies in the same amount of time. That's how you think of this. You hold the time fixed, and if you have more cats, they catch more bunnies. And so you get there. So the answer would be 3 minutes, I think. I did want to say this question for another reason though, which is about like the realism that you have in these situations. And this is something that I'm playing with right now because I'm thinking about these scaling problems. This is what I call a scaling problem, where you're going to scale the number of cats and bunnies. Scale means you multiply by the same amount. So I'm going to scale these two by some factor. And it turns out that not all things in life scale. And something that I was just playing with last night was what we're going to do with our new feature on Novid, which gives some information that comes through the network. And it turns out that on networks, some things don't really scale. In fact, I'll tell you what I think is the real thing you need to pay attention to for this problem. If you have cats catching bunnies, is it really linear? What usually is the situation, if you're trying to catch some bunnies, is the time it takes, is the amount of time it takes to catch the last one. Do you know what I mean? It's like when things are starting to run away, imagine what you had if you had 100 bunnies. What would they all do if 100 cats showed up? the bunnies would start running in every possible direction. Okay? And how long would it take to catch the 100 bunnies? It's really how long it takes to catch the last bunny, if you know what I mean. What I'm trying to say is that somehow, if you want to catch something, the hardest thing to catch is the last one. Where do you put the bunny? That is a good question too. But so whenever you're playing a problem, whenever you're playing a game in real life where you're worrying about catching the last one, whether it's the last bunny, or whether it's the last person who's COVID-19 positive, or whether it's the last whatever, actually oftentimes things don't really scale. They don't just like scale by multiplying by the same thing. So anyway, the best analogy for this, if you're curious, is there's a problem, a famous problem called the coupon collector problem. And that has to do with collecting coupons. Back in the day, you cut coupons out with scissors out of paper. But the coupon collector problem tells you that not all things just scale normally. In fact, there's something called a logarithm that comes in. Anyway, so I just had enough fun with these cats and bunnies. Let's go find some other problems. Oh no, Jacob Flint. What about one cat, 100 bunnies? Indeed, then the realism of this problem starts to really drop off because exactly what is the cat doing to the bunny? Wesley Wren has asked a problem that looks like algebra. Let's try it. Wesley Wren says 1 over A minus 1 over B equals 1 over A plus B. Okay? And Wesley Wren has a question. What is A over B plus B over A? Oh no! How can I do this? You only gave me one equation and two unknowns. One equation and two unknowns. And I'm supposed to figure out what they are? Well, not necessarily. I apparently need to figure out what this is. So let's go and play with this a little bit. Let's go and simplify this. Simplify meaning put it over common denominator, AB, A squared plus B squared. Yikes! I don't like this. I don't like the look of this. The reason I don't like the look of this is what's going on over here. I'm guessing you have a typo in the problem. Okay? So I think you have a typo in the problem because if I want to take this equation, what it tells me is it tells me that B minus A over AB is equal to 1 over A plus B. So if that's the case, I could multiply by A plus B, which is the same as B plus A. I'd get B squared minus A squared over AB equals 1. So now what I'm wondering is what you actually meant to ask B over A minus A over B? Right? Like this thing here is B over A minus A over B. This is 1. By the way, that's pretty cool. It's pretty neat that from here we could get this. So I'm going to say that if you meant to ask me what's B over A minus A over B, then I would say the answer is 1. But if you ask me what's A over B plus B over A, then my hunch is I would say there's a lot of different possible answers. And the reason is because, this one will be 1. But if you just go and mess around with A's and B's a little bit, it would be easy to get numbers that are not 1. Why do it would be easy to make this guy change. Why? Because if this is 1, then I can tell you what this is in terms of this guy. Right? If B over A minus A over B is 1, then B over A plus A over B, B over A plus A over B is 1 plus 2A over B. Because I have to plus 1A over B to get rid of this thing altogether, and then I plus another A over B, and it becomes a plus sign. But now that you see I get plus 1 plus 2A over B, I should have lots of ways to kind of mess around with my A's and B's to make the A over B part be bigger or smaller. Why I say I have some room to move around is because I have 2 variables and only 1 equation. Whenever you have 2 variables and 1 equation, you're actually able to kind of move you're almost moving along a line. Not a line, but you're moving along some kind of a track as your A and B both change. So I see that some people are asking, can I repeat, please? I think you're maybe asking, like, how do I know that I have lots of different answers? The way I get lots of different answers is just by saying, from here I have this particular piece. I multiply both. I simplify. This is b over a, b minus a over ab. That's the same as this. Then I multiply by a plus b, and I get this, because b minus a times b plus a is b squared minus a squared. Now I have this. And then now I simplify by dividing by the b on this side, and I get a b over a. And then minus the a squared over ab, divide through by a, is a over b. So I get this. And once I have this piece, since it's a minus sign and I want the thing with a plus sign, then I can actually go and put that b over a plus a over b is the 1 plus 2 of these. Okay? And so that's actually how I know that I can get lots of different stuff. Because if I made the a to be, I don't know, like some number, there would be possibly some b that matches it. But you move the a by a little bit and the b changes too. I think. Oh, wait! No! Ah. Wait, yes or no? Now I'm a little bit curious. No, not useful. Right, I was going to say if I multiply by something, this will become nice. No, I'm going to say I think that the answer is there's lots and lots of different answers here. So I'm going to guess that when you ask me the question, you might have meant to ask me this one, and then I'll give you a straight answer. All right. So let's go and what else should we do here? Oh, wow, people are trying to ban people who yell. Are you trying to ban me? Sometimes I yell when I get too excited. Other questions. Oh no, Ethan Gung, you're playing this one? Oh no, does anyone know? What's the next letter? Otfs. Otfs. What's next? This is a sequence. O, T, T, F, F, S, S. Should be T? Are you sure? Ah, I see some people figured it out. It's E. I think it's E. I don't know if it's E. We'll find out soon. 1 starts with an O. 2, 3, 4, 5, 6, 7, and 8. So I think that's the answer. I think this is cool. I think it's a funny puzzle. Thanks for sharing this puzzle. Why are we doing this puzzle? That's a good question. Somebody shared it. It looked kind of cute. All right. What else can we do? Offcent. Ah, it looks like you're saying otter scent. Sort of does look like that. All right. Well, so unfortunately, actually, that has finished this whole session. Let me just finish with this last one. I saw some people asking me things like, how do you do math if you're under pressure and you're stressed out? What would you do? Well, I think that I hope that by watching this thing, you have some idea of how I do math when I'm stressed out. I have 200 plus people watching us attempt to puzzle through arithmetic. And thanks, Umesh. Thanks for asking. You were the one. How to stay calm under pressure and do mathematics. I think the main thing is to have confidence in yourself. And I think that all of you who are watching this stream, you should have confidence in yourself. If you can keep up with the kind of stuff we've been playing around with for this hour, you're pretty good. And when I say confidence in yourself, it's the confidence that says you understand why all the steps work. You understand that if you get a wrong answer, all you have to do is to go back and figure out where in that logic was it wrong. And to have the confidence that you would be able to find that if you wanted to. Now, of course, if you're talking about an actual contest, clearly the thing to do is to eat enough bananas, according to the chat. But I think what we're going to say is if you're in a test or if you're in a contest, I think the important thing is just to be able to tell your brain to get rid of distractions. That's just good for you in general. Whether it's a math contest, math test, or anything else, just get rid of bad thoughts. They'll never get you anywhere. And then after that, then what you need to do is you need to go and have that confidence that if you just went and thought through it, you'd figure it out. And that's actually what makes me willing to try to do this stuff with you guys live on camera, where I basically look over here and say, hey, here's a question. Let's go play with this. I know that there's a decent chance I'll get it wrong. But at the same time, I know that there are enough people here that they'll catch right away that I multiplied some numbers and got 140 when it was supposed to be 70, and everyone will call me out on that, then we'll fix it. And then even if we get the wrong answer at the end, we usually can figure out why it's wrong and go back to right. And that's why math is fun. Okay, well, that finishes the live stream for today. I'll be back, as you know, every single day that we're seeing this kind of a crowd coming. You know, I'm inclined to come. If the crowd gets bigger, I'm inclined to come even more. But tomorrow, I'll definitely be here, 4 o'clock to 5 o'clock. See you.